Dr. Y. Sarada, Professor, Department of Mathematics, Anna University. Her area of specialization is applied probability and stochastic modeling. She has about 25 research publications in national and international journals. She has guided students for research projects. She has delivered lectures in her area of specialization in many institutions.
Welcome to the UGC lecture series on queuing and reliability. Presently, we are looking into the queuing models, particularly the Markovian queuing models. We got started with the machine interference model or the finite source model. This is model 6. In the Kendall's notation, MMR GDKK. Arrivals are Markovian, the departures are Markovian, namely the service time is exponential, that is the second index, and the third index speaks about the number of servers in the system. Totally there are capital R number of servers in the system, and the queuing discipline is general. We have the capacity of the system to be K and the capacity of the source, that is also restricted to K. And in general, the finite source models are suitable for modeling machine interference model. In these models, the customers are the machines which break down, and they come to the servicing facility to get repaired. Number of servers is R, that is to be interpreted as the repairman. So, we have R to be denoted as repairman, K is the capacity of the system, and source is also finite, namely the capacity of the source is K. This is where the machines come from. Totally there are capital K number of machines, and as and when each machine breaks down, it comes to the facility center, repair facility center, and it gets repaired by the repairman or the server and then put back into operation and so on. So, we will see the rates that are to be defined for this model, and the procedure is as before. We will be considering the generalized Poisson queuing model, the balance equations, and then we derived the steady state probabilities of finding n customers in the system, namely P n, and we substitute the values of lambda n, mu n which are assumed for this model in those expressions and try to get P n, and then if needed we are to determine the P naught probability of finding no customer in the system and hence the performance measures. So, let us go about it. So, lambda is defined as the rate of arrival. Since the arrivals are the failed machines, we describe lambda to be the rate of breakdown per machine, and hence lambda n, that is when there are n customers in the system, the arrival rate is defined as k minus n times lambda. Why do we write k minus n? Totally there are k machines that are operating, and when there are already little n machines in the system, those n machines are nothing but the machines that have failed. So, anymore given that when there are n customers in the system, so how many more machines are there which are operating? So, that is totally k minus n. So, anymore if any machine breaks down, it has to be from that k minus n, and hence we write lambda n to be k minus n into lambda, where n is between 0 and k, because we are restricting the capacity of the system here also to be k, and remember the capacity of the source or the population is finite, even there we have k. So, capacity of the system, capacity of the population, both are equal to totally k, and number of services or number of repairmen is capital R. So, we will see the service rates now. mu n is defined as n into mu when there are n customers in the system. This n lies between 0 and r, and we have capital R into mu when n is between capital R and k, and the rate is defined as 0 when n is greater than k. Here if you observe, this model is a mixture of the finite server model and the finite capacity model. Only thing, the additional feature of this model is the capacity of the population is also finite, and that is equal to the same number as the capacity of the system. So, when you write the service rates, it is similar to the MMCN model, except that we do have the restriction that even the total number of customers that could arrive from the population is restricted to capital K. Hence, we have mu n to be n into mu, where n lies between 0 and r, and the rate is defined as r into mu when n is greater than r, but of course less than k. So, once all the k machines are into the repair facility, there cannot be an arrival to the system. Hence, we define the service rate to be 0 once n is greater than k. So, our next approach, and similarly here if you see the arrival rate, we define it as k minus n, because those are the number of machines that would be available in the population to break down and come to the service facility. And once you have totally k of them, all k of them, which is the restriction from the source, to be available in the repair facility, then we have lambda n to be 0 since n is greater than k, because there cannot be any machine that could be possible to arrive into the servicing facility. So, with these definitions of the arrival and the service rates, we have to now get Pn, the probability of finding n customers in the system in the steady state. So, for this we borrow the birth and death model equations, and hence Pn. Basically, it is the Pn that we had seen earlier, the derivation. So, we will use that probability and plug in the expressions for the various values of lambdas and mu n's, and try to get a compact expression for the probability of finding n customers in the system in the steady state for this machine interference model. So, consider this generalized Poisson queuing model, namely MN-MN1 GD infinity infinity model, where Pn we obtained it as lambda naught, lambda 1, lambda 2 and so on lambda n minus 1, whole thing divided by mu 1, mu 2, mu 3 and so on mu n into P naught. Now, n can be starting from 0, 1 to 3 etc., but after substituting the expressions for lambda naught, lambda 1 and so on lambda n minus 1 and hence the mu's, we get Pn to be Kcn rho power n into P naught. What is rho? As before, we have rho is nothing but lambda by mu, where n lies between 0 and capital R. Also, in the case when n lies between capital R and k, we have the expression for Pn to be Kcn n factorial rho power n by r factorial into r power n minus r into P naught. Now, as usual, we have to find the probability P naught. So, we use the normalizing condition and obtain P naught as sigma n equal to 0 to r Kcn rho power n plus sigma n equal to r plus 1 to k Kcn n factorial into rho power n by r factorial into r power n minus r, the whole inverse. So, we will try to get these expressions now. So, we have been given lambda n is equal to k minus n into lambda. This is the case when 0 less than or equal to n less than or equal to k, where k is the capacity of the system as well the limit on the population. and then we have mu n, the service rates when there are little n customers in the system, as n into mu, and it is r into mu, and defined as 0 in the 3 cases where we have 0 less than or equal to n less than capital R less than or equal to n less than or equal to k, and then it is defined as 0 when n is greater than k. And further, from this generalized birth and death process or the generalized Poisson queuing model, we had Pn to be defined as lambda naught, lambda 1, etc., lambda n minus 1. Totally there should be n terms in the numerator and in the denominator also, supported by mu 1, mu 2, mu 3 and so on, mu n into P naught. So, now when you plug in these values, for example, here for this model we have P n equal to, when n is 0, you start with k times lambda into, when n is 1, for lambda 1 we have k minus 1 into lambda, when n is 2 we have lambda 2 as k minus 2 into lambda and so on. The last term for lambda n minus 1 in the numerator will become k minus of n plus 1 into lambda. So, this accounts for the totally n terms there, and in the denominator we have, what we are writing here is, in the case when 0 is less than or equal to n less than r. Why we have this split up? Not because of mainly lambda n, but because of the service rates mu n. So, we have mu 1 is, this is the case when 0 less than or equal to n less than r, the first one, when mu n is written as defined as n mu. So, we write it as 1 into mu, which is mu, and then 2 into mu, 3 into mu and so on. The last term would be n times mu, but here we have this term P naught hanging. So, we have the expression out this also comprises of the n terms. So, we will see the next classification. In the case when r less than or equal to n, which is less than or equal to k. So, in this case the numerator becomes, again it is going to be k minus 0. So, k lambda, it is similar, k minus 1 into lambda, k minus 2 into lambda and so on. We have k minus n plus n minus 1. So, which becomes k minus of n minus 1 is nothing but k minus n plus 1 as written before into lambda, the whole thing divided by, once again we have when r is equal to n. So, the first term itself here starts with n equal to r. So, when you put n equal to r, what is the rate, how is it defined here in this second case? So, it is r into mu. So, the first term would be r into mu, anymore n is greater than r. So, this is similar to how we wrote for the multi-server model MMC. So, once the number of servers are greater than C or equal to C, the rate was defined as C mu. So, we will be writing it as C mu into C mu and so on. So, as a similar interpretation here, you have instead of C, it is capital R here. So, we have to write it as R mu and so on. R mu written as n minus r times. Can you guess what it would be for the remaining terms here? Remember here the number of servers is less than the capacity of the system or the limitation of the source. So, when n is lying between capital R and k, we are presently trying to write the mu n's, that is the denominator in trying to find the steady state probability of finding n customers in the system. So, let us get back where we stopped. So, here we have numerator, we wrote it as k into lambda, k minus 1 into lambda, k minus 2 into lambda and so on, k minus of n minus 1 into lambda. So, this expression later on would be similar to what we wrote here, namely k minus n plus 1 into lambda divided by mu 1 here. Instead of mu 1 here, what is that we have? N is capital R. The least value in this case is n equal to R. So, you have to write mu R, when mu R is nothing but defined as R into mu here. So, we start with R into mu, then R into mu when n is R plus 1 and so on. So, till how much you would have R mu, you will be writing n minus R times. Now, when more than that, we start with, say, next term would be R minus 1 into mu, and then next term would be R minus 2 into mu and so on. Say suppose n equal to R minus k or n equal to R minus k minus 1. So, then you will have here the last but one term to be equal to 2 mu and the last term would be 1 into mu. So, this is when you have, say suppose n equal to k minus 1. Why I am taking this case is, you have this restriction out here. The case we are writing is n lies between capital R and capital K. So, the last but one value here would be k minus 1. So, when you put n equal to k minus 1, so how is mu n defined? Say k minus 1 into mu. So, in this case you would have the servicing rate to be 2 into mu and then 1 into mu. So, in this case we have R mu appearing in the denominator n minus R times, and then the remaining terms would be starting from 1 into mu, 2 into mu and then up to k, the first R minus 1 terms. When you write n equal to R, we are accounting from mu 1, mu 2 and so on up to n into mu, right, mu 1, mu 2 and so on mu n. So, for mu 1 it is mu, for mu 2 it is 2 mu and so on up to R minus 1, there is no problem. From n equal to R onwards, you will be writing the service rates to be R into mu and so on up to R into mu. Even when n equal to k, it is a case where k is greater than R. So, the service rate has to be written as capital R into mu. So, we have this term out in the denominator. Our next step would be to simplify this and write it compactly. So, we have Pn now written as, in the numerator we had k lambda, right, k minus 1 lambda and so on, k minus n plus 1 into lambda by, we had 1 into mu, 2 into mu and so on, n into mu. So, this is the case when 0 less than or equal to n less than capital R. Now, how does this term simplify to? Here this will become, you can write k, k minus 1 and so on, this up to k minus n plus 1 as using the combinatorics following, namely k factorial divided by k minus n factorial. So, and how many lambdas are there here? N of them. Product of n lambdas will give us lambda power n divided by, from the denominator we have 1 into 2 into and so on up to n, and the mu is also taken n times product. So, you will get this as compactly, if we write k factorial by k minus n factorial into lambda power n by mu power n into this whole thing need to be written as n factorial. So, this is the case when 0 less than or equal to n less than r. Now, the same thing what we had in the case when n lying between r and k is k lambda, k minus 1 into lambda and so on Similarly, k minus n plus 1 into lambda divided by r into mu, right, r into mu taken, this product taken n minus r times, and the remaining r terms will take the form r minus 1 into mu, r minus 2 into mu, and so on up to 1 into mu. Of course, we had everywhere p naught. I will write this p naught here. So, this is the case we are writing when n is between r and capital K. So, this expression now will become, as before, numerator becomes k factorial divided by k minus n factorial, and as usual lambda power n divided by mu power n, and what we would be having extra is here r factorial comes from the latter part, namely from terms when mu 1 to mu capital R. So, mu power n r factorial and r power n minus capital R, this whole thing into p naught. So, mu 1, mu 2 etcetera mu r, that is mu r shall I write here. So, this will accommodate for those r terms, and the remaining n minus r terms will have r mu. See, I have written here r terms, here n minus r terms or times. So, this will be the case. So, this we further rewrite using combinatorics. This is nothing but, now I have to replace lambda by mu to be equal to rho, that is first observation. And then what is KCN in general? KCN is k factorial by n factorial into k minus n factorial. KCN, the notation is either this or it is, we can rewrite this as say KCN. So, it is k factorial by n factorial into k minus n factorial. So, what we have here in these expressions, k factorial by k minus n factorial. So, what does that equal to now? That is equal to KCN into n factorial. You take the cross multiplication here. So, we rewrite again Pn is equal to KCN rho power n into p naught when 0 less than or equal to n less than capital R, and it is equal to KCN n factorial divided by r power n minus r, r factorial rho power n into p naught. This is the case when r is less than or equal to n, less than or equal to k. When n is greater than k, anyway all these values will be zeros, because there is no arrival which is possible and hence no service also. So, we get 0. Next aim would be to find p naught. So, what is the procedure? We have to use the normalizing condition that sigma n equal to 0 to infinity p n is equal to 1. But then here we cannot write the upper limit to be infinity, because we are dealing with the finite capacity, finite source model. So, the upper limit has to be restricted to capital K of them. So, once again, but we have to split this summation, where we have to break is because this is a multi server model too. So, the number of servers is capital R. So, write the summation as two summations, one is from 0 to R, the other one is R plus 1 to capital K, or we include 0 to R minus 1 plus R to capital K, because whether you write R here or they are either in the first summation or in the first summation, it does not make much difference, because you have from R to capital K, the rate is R into mu for the service. So, let us see how to find this p naught now. So, we have this normalizing condition rewritten as sigma n equal to 0 to capital K P n equal to 1. So, this in turn becomes, this implies that when you write the terms, this is nothing but summation n equal to 0 to say r minus 1 P n plus sigma n equal to capital R to capital K P n is equal to 1. Now, when we substitute these expressions, the value we get is the following, namely P naught equal to summation n equal to 0 to capital R minus 1 K C n rho power n into P naught plus summation n equal to capital R to capital K n factorial divided by R factorial R power n minus R, and we have a KCN here into P naught, this is equal to 1. Actually, we expanding the summation what we had, that is rewrite here sigma n equal to 0 to capital K P n equal to 1. So, that is rewritten here as this. So, now here P naught is common in both the terms, pull out that P naught. So, this implies that P naught times summation n equal to 0 to r minus 1 K C n rho power n plus summation n equal to r to k K C n n factorial divided by r factorial r power n minus r equal to 1. So, this implies that P naught equal to the whole expression is in the denominator, n equal to 0 to r minus 1 K C n rho power n plus sigma n equal to r to k K C n n factorial divided by r factorial into r power n minus r, the whole inverse. So, this is what we had seen in the expressions there. So, this is what we had, the expressions. So, now let us look into the performance measures. LQ is defined as sigma n equal to r plus 1 to capital K n minus r into P n, because number of machines in the queue is the quantity that is being dealt with on an average, and LS is defined as LQ plus r minus r bar, where r bar is sigma n equal to 0 to capital R minus n into P n. LS is defined as LQ plus lambda effective by mu, where lambda effective is mu into r minus r bar, or it is rewritten as lambda times k minus Ls, which is nothing but expectation of lambda times k minus capital N. Now, here lambda effective is to be written here because we have this restriction on the capacity of the system. Hence, we need to use lambda effective in order to find the performance measures. So, what we have done till now is we have looked into the sixth model, namely the machine interference model. We got started with the rates, defining the arrival rate and the service rate, and went on to get the steady state probability of finding n customers in the system in the steady state, and then we have obtained the P naught and hence the performance measures using the Little's formulae. Thank you.